So I want to do an example today for curve sketching, or this is sometimes referred to as detailed graphing. Now, depending on who your instructor is, there might be a long list of things that you're supposed to include on the graphs. I'm kind of going to go over the basics that everybody's going to need in order to sketch a graph of this. Now, I want to start by saying this is a polynomial function, which means we could use our pre-calculus skills to get a good idea of what this graph is doing anyway. And that's usually where I want to start with detailed graphing. So I'm going to start with the things that we could have done in pre-calculus, which means I'm looking for y-intercepts, x-intercepts. And what's sometimes referred to as the end behavior, or in the case of calculus, we know that to mean the limits as x approaches positive and negative infinity. So for the y-intercept, we're always finding this the same way. I'm going to let x equal 0 and see what we get for y. Well, in this case, I'm going to have 0 cubed times 0 minus 2, and overall, we're just going to end up with 0. Now, in terms of our x-intercepts, those are always happening by setting y equal to 0. We usually are hoping that the function's going to factor. Well, I already gave it to us in factored form, so one less step we're going to need to worry about. If 0 is equal to x cubed times x minus 2, that means I've got two intercepts happening, one when x is 0 and one when x is equal to 2. Now that other thing that I mentioned, that end behavior, that's what we would have called it in pre-calc, but in calculus, if I'm looking for that limit as x approaches positive or negative infinity, what we're really checking for there are horizontal asymptotes. So I'll just abbreviate that HA. So if I take the limit as x approaches either positive or negative infinity here, but let's start with the positive infinity case. I've got x cubed times x minus 2. If I plug in a very large positive number, well, infinity cubed times some more infinity, that whole thing is headed to infinity, which means that on the far right-hand side of our graph, we should be going up. Now, if I check the limit as x approaches negative infinity for x cubed times x minus 2, well, I'm still going to be plugging in a very large number and cubing it and then multiplying it by that same very large number. So overall, I know this is headed to infinity. We just want to be careful to check our signs. Well, negative cubed would give me a negative, but then multiplying by another negative, we've looped back around to a positive. So this is also going to positive infinity, which means on the far left-hand side of my graph, I should be going up. This is enough to get our pre-calculus sketch going. I know that I've got x-intercepts at 0 and 2. And I know that I've got a y-intercept at 0. Well, that one's already on my graph. And I know that end behavior. So on the far right-hand side of my graph, I've got to be headed up. And on the far left-hand side of my graph, I've also got to be headed up. Now, there's a trick that we may or may not remember from pre-calc. And that comes down to looking at the powers on my different pieces. So I know that that x cubed is what gave me the x-intercept of 0, which means that as I pass through this, it should behave kind of like a cubic. So as I'm passing through, I'm going to have a little bit of a bend like a cubic. When I've got that x minus 2 piece, that's to the first power, or it's a linear term, which means as I'm coming over here to 2, as I pass through that intercept, it should look approximately linear. Now that's about all we can do with our pre-calc skills, but there are two calculus things that we now want to investigate. I'm just going to smooth this edge of the graph out a little bit. Okay, so zooming back to our calculus skills, one of the things that we couldn't do in pre-calc is to know exactly how low this went, or to verify that we should have a little squiggle in the graph here. And that squiggle in the graph, that's going to be our inflection point. And this point down here, well, that's both a relative minimum and an absolute or global minimum looking at the curve. And I'm going to figure out where exactly that local minimum is by taking a look at our first derivative. Since we've already got our intercepts up there, I'm going to go ahead and erase them. Okay, first derivative, I'm coming in here and looking for my f prime. We've got two choices. We could do a product rule on this. I'm going to choose to multiply it out and avoid the product rule. So I'm going to rewrite this to say x to the fourth minus 2x cubed. Now I don't have to worry about a product rule. So my derivative here, got 4x cubed minus 6x squared. Now that first derivative, it's going to tell me where the graph is increasing and decreasing, and if we get a number line going, it's going to show us where our relative maximums might be. So the first thing I want to do with that derivative is set it equal to 0 and get it factored. Looks like I can pull out a 2x squared, and then I'll be left with 2x minus 3. So now I know that my first derivative is 0 when x equals 0, and it's also 0 when x equals 3 halves. Now what I like to do with that first derivative is now get a number line going. I'll put my 0 and 3 halves on the number line, and then I'm going to do test points in between to figure out whether my first derivative, and I'm going to go ahead and label my number line as f prime so I remember that, whether my first derivative is positive or negative. If I pick a test point in here, like maybe x equals 1, we can plug it in either to that first version of the derivative or the factored form. It shouldn't matter. I'm going for the top. So if I plug in 1, that's going to be 4 minus 6, so it should be negative, meaning my graph should be going down between 0 and 3 halves. If I choose a test point out here, say x equals 5, then, well, now I'm going to cheat and use my factored form because I know that something squared is always positive, so I don't even have to worry about that part. So if I plug in the 5 here, 10 minus 3, that's also positive, so I know my graph should be going up. Now out here, if I choose a test point like, let's say -1, oh, it's a toss-up of which one to plug it into. I'll go for the top. So -1 cubed, that's going to give me a negative number. So I'll have -4. -1 squared is going to make that a positive number. So plus 1 times a -6. So I've got -4 minus 6. So overall this is going to be negative, which tells me my graph should be coming down. Now let's make sure that makes sense with our pre-calc version. Well, looks like we did pretty good. So everywhere I know that my graph should be coming down as I approach 0, which it is, and then still going down until we get to an x value of 3 halves. So now we know that this point here has an x value of 3 halves. Now in order to get the y value, we'd have to plug that back into the original function. I'm going to be lazy today, and I'm going to write that as f of 3 halves. That way I'm accurate, but I didn't spend the time plugging in that fraction. So I now know also that that's a relative minimum, which we can also see from the number line here. Now the next piece that I said is we should verify that there is that squiggle at 0 or that inflection point. And the way we're going to do that is by checking our second derivative. I'm coming back around here. I'm going to go back to this one, not my factored form again, because I don't want to have to worry about product rule. So f double prime, I am looking at 12x squared minus 12x. So that second derivative, if I go ahead and set that equal to 0, looks like I can factor out a 12x, and then I'd be left with x minus 1. So it looks like I should have 2 inflection points, potentially, one at 0 and one at x equals 1. just because my second derivative is 0 doesn't guarantee that it's an inflection point. We actually need to check whether we change concavity on either side of those values. And to do that, I'm going to do a similar thing to what I did up above, but this time my number line is going to be for the second derivative. I'll go ahead and put 0 and 1 on that number line, and then choose some test points. I'll start out here this time. If I plug in x equals 2, and I'm going to use the factored form, 12 times 2, that's positive, and 2 minus 1 is also positive. So I know over here, this should be concave up. If I pick a number between 0 and 1, for me it's a little easier to think about it as 0.5 instead of a half. So I'm going to choose my test point as 0.5. If I plug in 0.5, 0.5 minus 1 is definitely negative, but 0.5 times 12 is positive. And a positive times a negative will overall give me a negative, and we should be concave down. If I pick a test point out here, like maybe -1, plug that in, well, -1 minus 1, that'll be a negative number, and 12 times -1, that's also a negative number. So I've got a negative times a negative, leaving me a positive overall. So it looks like both 0 and 1 should be x values where we have an inflection point. Let's make sure that our graph shows that. Well, coming over here, I think the inflection point at 0 I did a pretty good job with, but I think it's a little harder to see my inflection point here. So I'm going to go ahead and label it. I'll put a point over here. This is my inflection point, and we know that that inflection point was happening when x equals 1. 1 is pretty easy to plug into my original function, so this time I'm not going to be lazy. I'm going to plug it in and get the y value. So I've got 1 cubed, and 1 minus 2 is going to be a -1. So that should be happening at 1, -1, which also matches up pretty well with our graph. So this would be my complete picture for detailed graphing of this polynomial.